In this lesson, Electromagnetic Induction, Part 2, Moving the Magnet, we will study 3 parts. Number 1, Moving a Magnet. Number 2, we will study the transformers and how they work. Number 3, how electricity is distributed by the national grid. In the first part, we studied how an induced current is produced when a wire is moved cutting the magnetic field lines of a magnet. Actually, this is not the only way to produce an induced current. If the wire in the form of a coil of many turnings is fixed, and the magnet moves towards the coil, this will also produce an induced current. Reversing the motion of the magnet by taking it out of the coil will produce an induced current in the opposite direction. This phenomenon can be explained like the previous case, as the wire of the coil cuts the magnetic field lines of the magnet. But a more scientific and more general explanation must be discussed. Now we need to know the reason why moving a magnet towards a wire can cause an induced current. Remember, in the first part, our case was a moving wire with a magnet in place. This process produced an induced current, which is explained as follows. The metallic conductor wire cuts the magnetic field lines of the magnet, causing an induced current in the wire. But now in part 2, the magnet is the moving part, while the wire in the form of a coil is the fixed part. And this also can be explained the same way. The metallic conductor wire cuts the magnetic field lines of the magnet, causing an induced current in the wire. But here we can have a more scientific and wider explanation that prepares us to have more advanced applications. For this case, we can say that the metallic conductor wire is exposed and affected by a changing magnetic field. You can also say a variable magnetic field, causing an induced current in the wire. In this part, we will study Lenz Law. These are the 2 ways we know until this level to produce an induced current in a wire. The first is to move the wire in a fixed magnetic field. In this way, as we said in the first part, the direction of the produced induced current is given by Fleming's right-hand rule. This rule is discussed in the first part, moving the wire. The second way we know until now to produce an induced current is to move a magnet near a fixed coil. The direction of the induced current produced by this way is given by what we know as Lenz's law. Let us understand this law in details. When a magnet moves with its magnetic field near a coil, towards or away from it, this produces an induced current in a certain direction. According to what we had before in the electric motor, every current makes its own magnetic field. So the produced current in turn will create its magnetic field around the coil. It's clear now that we have 2 magnetic fields. The magnetic field of the magnet that causes the current, and the magnetic field around the coil that is caused by the current. Lenz's law tells us that the magnetic field caused by the induced current will oppose the effect of the magnetic field of the magnet that causes the current. So according to the previous explanation, we can say that Lenz's law states that any induced current caused by a changing magnetic field will make its own magnetic field that opposes the effect of the magnetic field that created it. We have 4 examples. In the first example, this is the coil, and this is the magnet that will move towards the coil. This sure will cause an induced current in the coil, but the question will be, in what direction? If the coil wants to oppose the effect of the magnet that is moving towards it with the north pole, the coil must generate a north pole facing the coming north to make repulsion and resist the motion of the magnet. It's clear that the far end of the coil will be a south. With the aid of right-hand grip rule, The current will be in the direction shown by the right hand fingers when the thumb points with the north. Example number 2. In this example, the magnet is approaching the coil, but this time with the south. This will cause an induced current in the coil, and again the question will be, in what direction? If the coil wants to oppose the effect of the magnet that is moving towards it with the south pole, the coil must generate a south pole facing the coming south to make repulsion and resist the motion of the magnet. It's clear that the far end of the coil will be a north. With the aid of the right hand grip rule, the current will be in the direction shown by the right hand fingers when the thumb points to the north. In example number 3, the magnet is moving away from the coil with the south. This will cause an induced current in the coil. If the coil wants to oppose the effect of the magnet that is moving away with its south, the coil must generate a south pole facing the north pole to make attraction and resist the motion of the magnet away from the coil. It is clear that the far end of the coil will be a north. With the aid of the right hand grip rule, the current will be in the direction shown by the right hand fingers when the thumb points with the north. The last example, number 4, the magnet is moving away from the coil with its north. This will cause an induced current in the coil. If the coil wants to oppose the effect of the magnet that is moving away from it with the north pole, the coil must generate a north pole facing the south to make attraction and resist the motion of the magnet away from the coil. The far end will be a south. For the 4th time, using the aid of the right hand grip rule, the current will be in the direction shown by the right hand fingers when the thumb points with the north. Still on the second method of producing induced current, moving the magnet near a fixed coil. Now it's time to know how to get larger current by this way. Increasing the number of turnings of the coil can increase the intensity of the induced current produced by this method, even if we use the same magnet with the same speed. Also, in this case, using a stronger magnet can cause a stronger current. And finally, moving the magnet faster into or away from the coil can produce a stronger current. Now we nearly finished everything about the second method of producing induced current, which is moving the magnet near a fixed coil. So it will be a good idea to have a comparison between the two methods we have. The animation shows the way they produce the current. If we talk about the case, the first one shown by the diagram on the left is a case of moving wire and a fixed magnet. On the other hand, the case on the right is a case of moving magnet near a fixed wire or a coil. If we talk about the explanation, the induced current produced by the first case is explained as the metallic conductor wire cuts the magnetic field lines of the magnet, causing an induced current in the wire. It's clear that our keyword is cuts, but in the second case the induced current is explained as the metallic conductor wire is exposed and affected by a changing magnetic field. You can also say variable magnetic field, causing an induced current, and it's clear that our keyword is the changing magnetic field. And finally, if we talk about how the direction of the induced current can be predicted, in the case of the moving wire, it is given by Fleming's right-hand rule, while in the case of the moving magnet, the direction is given by Lenz Law. If you really understood the case of the moving magnet, you will realize that it is not the story of a moving magnet near a coil. It's the story of the presence of a changing or variable magnetic field near the coil. Any changing magnetic field near the coil will cause the induced current. In this part, we will know other methods of how to get a changing magnetic field other than moving the magnet. The first method is what we have just studied, and it's the original case moving the magnet into or out of the coil. Another method of getting a variable changing magnetic field is rotating the magnet near the coil. The rotating magnet will cause a changing magnetic field that can create an induced current in the coil. Another method to produce a changing magnetic field is an AC current. The blue coil is connected to an AC power supply. The AC current can produce a magnetic field which is continuously changing in both strength and direction. The changing magnetic field also can produce an induced current in the black coil. And the third case we just studied is the basic idea of the work of the transformers.